Welcome to this workload modeling video. Today we're going to show you how to use FC and iSCSI workload models. A workload model can be broadly defined in a storage context as a storage I/O requests made by application systems against storage infrastructure. When these requests are analyzed in terms of IOPS, read-write percentages, sequential versus random behavior, and block size distribution, then these characteristics can be used to model that workload. This model can then be used to emulate that workload to support activities across a storage lifecycle. The Workload Central homepage has a library section which contains default workload models provided by virtual instruments. Select Workload Models, which will enable you to construct and run a workload. The Workload Models part of the library lists the default templates provided with Load Dynamics Enterprise and enables you to add an instance of the selected model that can be modified, run, and/or deleted. The models in the library cannot be modified or deleted. The high fidelity FC and iSCSI workloads are identical, except that iSCSI currently has no MPIO capability. To clone a high fidelity FC or iSCSI workload, click the Clone button, specify a name, click the Clone button in the pop-up window. Under Start a New Test, click the Start button. The start and edit functions are very similar, and you can edit a project at start time. The difference is that in Start, changes are not saved to the project. However, if you edit and then save, the changes to the project will persist. The access pattern describes how frequently and by what means the storage is accessed. The first element is the command descriptor block length, or CDB for short, which shows the size in bytes of the header of the SCSI command. The OS sets this automatically depending on data block sizes or the size of the LUN being accessed. The most common sizes are 10 and 16. The default is 10, and 16 is usually used only for large data transfers, such as backups, or for LUNs larger than 2 terabytes. The slider in the data field describes the percentages of reads versus writes. The writes section describes what the write traffic will look like. You can select a constant request block size or a bin distribution of block sizes. If you specify bin, you can use the default settings or create up to 8 custom bins specified in kilo, mega, or gigabits. The expected average block size is displayed. Because the actual individual block sizes used in the environment might not be known, and only the average can be calculated. The sliders allow you to adjust the percentages of the different block sizes used until you get the ratio you want. Instead of using a bin distribution, you could also create a set of workloads, each for a specific block size, 4K, 8K, etc. Set their IOPS to maintain the same ratios as done here with the bins, and combine them into a single composite workload. When you use the bin distribution option, the block sizes supported by a particular array will affect the data reduction option in the data parameters section. If a block size is less than the minimum size supported by the array, those data blocks will not be reduced. Use the Configure Write Pattern slider to specify the percentage of writes that will be random or sequential for each worker in their own space. If there are multiple workers, sequential requests might appear more random, because the system cannot determine that multiple sequential requests are coming in from different sources. The number of asynchronous IOs specifies how many commands can be sent out on the wire at one time per worker. In this case, the recommended default, each worker is allowed to have 8 writes out independent of reads. When 8 writes are out on the wire, then one of those writes must complete before another can be issued. Configure IO region specifies where to write the data. If you specify a percentage, you don't have to make any adjustments if you change the size of the testbed or use smaller or larger LUNs. You can specify absolute values too. For example, stay within a cache area if you know the size of the cache, which can change from one system to another. One region is used for the write location. If you specify absolute, then only that size region, starting at the specified offset, is used. The values are specified in the text boxes. If you specify a percentage, then the starting offset and overall region are calculated by the workload. With temporal and hotspot workloads, you can combine multiple regions. However, these techniques are more complex. Specific offsets are generally not used or known, but they can have a significant impact on architecture. You can tune hotspots until cache and tier hits match those observed in production. In reads, there is an option to use the same read parameters as the specified write parameters. However, this option is not commonly used because input and output block sizes often differ, as does the balance between random and sequential I/O patterns. The same workload parameters apply to reads as well as writes: request size, random sequential read pattern, asynchronous IOs, and IO read from region. The number of asynchronous read IOs is independent of the writes, so the default settings allow 8 reads as well as 8 writes out on the wire, for a total of 16 read-write commands outstanding per worker. As with writes, when 8 reads are out on the wire, then one of those reads must complete before another can be issued. Multipath I/O currently applies only to a FC workload and not to iSCSI. Failover redirects traffic from inoperative to operational ports. Round robin distributes the load across all ports participating in MPIO, where each command is sent down a set of paths in order: path 1, 2, path 1, 2, path 1, 2, 3, 4, for however many paths exist in the multipath configuration. Least queue depth uses the least busy, quickest responding port for traffic. The number of commands outstanding on a particular port determines which path it uses. Asymmetric Logical Unit Assignment Reconfiguration, or ALUA for short, enables reports from a storage array to specify primary and secondary ports. If it's disabled, the workload ignores the primary and secondary allocations of the array and follows a specification in testbed, which performs negative testing regardless of the array specification. The error handling selection allows the scenario to restart without exiting if error conditions occur. Ignore errors gracefully is required if errors will be introduced during MPIO testing. Data parameters determines what actual data content is being written to or read from the disk. Constant generates the same data pattern repeatedly, either ones or zeros depending on the protocol, and is not often used. Sequential data counts up to a 64-bit number before looping. Each worker will be writing the same data pattern, so there will be as many duplicates as there are workers. Depending on the storage array's compression and dedupe algorithms, these duplicates will likely either be deduped or compressed. Seeded random is a randomly generated pattern that can be recreated, and you can specify the seed. Duplicates will occur for each system that has a specified seed, so if you write to 2 LUNs that are the same size with the same seed, the LUNs will be identical. There will be duplicates across the LUNs, but no duplicates within each LUN, and what's written is relative to the offset from the beginning of the LUN. Data reduction is the easiest way to get duplicates, and allows you to specify compression, duplicate ratio, and number of unique duplicates. Specify how much the data will be compressed by putting zeros within the block. Most algorithms work very well with this, but some don't pick it up, and it requires very little processing by the algorithm. The deduplicated size specifies how many duplicates and number of duplicates to be used. In this example, the ratio is 4 to 1, and the number of unique duplicates specifies the size of a pool of data for reuse at a 4 to 1 ratio. To maintain this 4 to 1 ratio, in addition to the pool of data that we reuse, we also intermix completely unique data that is never reused. Duplicate size is based on the block size, so if some 4K blocks are written and the array is based on an 8K block size data reduction, the 4K blocks will not be reduced. However, if the same bin distribution pattern is reused at 8K, then the 8K blocks will be reduced. Therefore, when setting up the dedupe ratio, keep in mind the block size specified by the array manufacturer, and set a higher value to deduct the amount of data below the block size that the array manufacturer can support. See request size in the write section. A pretest sets up the testing environment and normally includes preparing the file or object system and LUN so the workload can be run against it. For most arrays, it's important to have data on the disk, otherwise the array responds too quickly to both reads and writes. But once a pretest has been done on a test bed, it need not be rerun. Or you can just run the pretest by itself to get it out of the way, even if you are not ready to start the workload. The pretest will write to the section specified by region offset and region size, and also uses a specified request size. Unless data reduction is specified for the data content option, then we use a requested size specified by the bin distributions, so we maintain the mix of block sizes. The load properties section defines the number of concurrent workers, or connected users, as well as a maximum load or the number of IOPS or throughput generated. Ramp up is how long the test takes to reach the required load and number of workers, and ramp down is how long it waits for remaining transactions to complete before they are aborted. Generate the load maximum with at least one concurrent worker per LUN, because a worker works on only one LUN. For an even workload across LUNs, it's best to have the number of concurrent workers be a factor of the number of LUNs in the test bed. It's generally okay to have more workers than are needed because a test doesn't measure the time a command is in the queue before it's handed over to the wire. Therefore, it's better to specify too many workers than too few. A technique for visualizing exactly how performance degrades as workload increases is to set the actions per second, IOPS, or throughput, to twice the expected value the array can achieve, and to set a long ramp-up, such as an hour, so the performance degradation curves of increasing latency and leveling of IOPS can be observed. The tracing parameters option is disabled by default, and it shows the SCSI level portion of what's being sent on the wire. It's used primarily for debugging, to see why commands are failing on the array, and is similar to the capabilities of a protocol analyzer. You can specify how much to capture and whether it's a circular trace or only the first packets are traced. Sometimes only the header might be needed, and therefore only the first part of a frame need be captured. FC frames are 2K long, so if, for example, only the first 64 bytes are needed, then more frames can be captured. The test configuration specifies how long the test will run, and optionally retrieve the summary file and/or capture LUN usage. Run it on specifies the test bed on which to run the workload. At start time, you can accept a full test bed as is, or you can remove links and run the test on only a subset of the environment. In Conditions and Actions, which is a common module, you can set conditions to stop the test automatically because of specified criteria, either while it's running or after it completes, and mark it as successful or failed. In Description, which is a common module, the description specified here appears in the legends of generated reports and charts.